Let's do a little review of vectors. Vector components, vector addition, dot products, and cross products. You might want to come back and look at this video again later on in the quarter as we start incorporating more two-dimensional problems into our curriculum. But for now, we'll start out with vector components. Any vector can be written as the sum of other vectors. Here's a vector. Why don't you write it as the sum of two other vectors? Which two vectors would you pick? Did you pick these two vectors? Is the red vector the sum of these two blue vectors? Yes, it is. Maybe you picked these two vectors. Is the red vector the sum of these two green vectors? Yes, it is. My guess is you didn't pick either of those pairs. My guess is you picked these two vectors. Is our red vector the sum of these two gray vectors? Yes, it is. We could have used any of these sets to break up this red vector into the sum of other vectors. But you know already that it makes sense, if we're going to break up a vector, to break them up into orthogonal components like we've done here. And what's the relationship we have here? Let's put an angle in. We'll call that theta. We know that A squared is going to be equal to the magnitude of F squared plus the magnitude of G squared, because this is a right triangle. We also know the magnitude of F is going to be A times the cosine of that angle, because it's the adjacent side. Adjacent over hypotenuse is our cosine. And we know that G, the magnitude of G, is the magnitude of A times the sine of theta. So we can break up a vector into its components using sine and cosine. Hopefully, this is review. If anything in this video is not a review and you need a little bit more explanation, check Khan Academy for a video where you can get a nice explanation of why the properties are the way they are. Here are two vectors, A and B, and we're going to add them. First, we're going to add them graphically, and then we'll use components. So to add them graphically, remember we add vectors tip to tail. We draw our coordinate system. And the first thing we do is we draw one of our vectors. We draw A. Vector A is going to look something like this. Then we come out to the tip of vector A. We treat this like a new coordinate system, and we draw vector B. Vector B would look like this. So we've just taken this vector and moved it here, and we've taken this vector and moved it there. We've kept the orientation the same, just moved it over such that the tail of vector B is now at the tip of vector A instead of the origin. And what is our resultant? It's this red vector. We start at our starting point, which is the origin, and we draw a vector out to the tip of the last vector. So that's the resultant. I'll call it C. And of course, when we're drawing these vectors, we use our protractors to get our angles just right, and our rulers to get the lengths of these vectors just right, proportional to the magnitude of each vector. So A has a length of 5, B has a length of 6.32. And then I get out my protractor and my ruler, and I can measure vector C. Then I would record what angle I'm measuring. Doesn't matter what angle you measure, just mark it so I know which angle you're measuring. In this case, I marked the angle with respect to the y-axis, so this would be approximately 26.5 degrees. Now when you're doing this, you can be really careful. You can draw a big, blow this up so it takes up your whole page, so your scale, it can be more accurate. You have less error that way, and be meticulous about your angles and your measurements, and you'll get very good results. But it won't be exact. We'll use components to add these vectors up, and we'll see what the exact results are. So I like to fill this table in. First, let's take a look at vector A. Vector A had a magnitude of 5, and it was at an angle with respect to the x-axis of 53.1. If this is a physics problem, you can pick your coordinate system at this point. But in this case, we were given an xy coordinate system, so we'll go with that. Our x-axis is our horizontal axis, positive to the right. Our y-axis is the vertical axis, positive towards the top of the page. So this is going to point in the positive direction, our a sub x, and it's going to be the magnitude of the vector times the cosine of 53.1 degrees. And our y component is also pointing in the positive direction, 5 sine 53.1 degrees. Vector B, 6.32 magnitude with an angle with respect to the negative y-axis of 18.4. So I'm going to break it up into its components. I'll use gray. We've got a component in this direction. That's our y component of vector B. And that would be pointing in the negative direction. And I would use the cosine of 18.4 degrees because the angle was given with respect to the y-axis. I'm going to make a right triangle here. And I can see that the angle that was given, 18.4, the adjacent side is my y component, and the opposite side is my x component. So this would be 6.32 sine of 18.4 degrees, but you have to remember to put in the minus sign if it points in the minus direction. And I like to do it this way because I don't understand the opposite and adjacent side of an angle more than 90 degrees. So I always pick an angle less than 90 degrees so I can picture which is the adjacent side, which is the opposite side, when do I use sine, when do I use cosine. When you do that, you have to manually put in the negative signs. It's usually better to do it this way if this angle was given. Then you don't have to do a calculation. If 18.4 is given with respect to the negative y-axis, just use it. Why do a calculation and maybe make a mistake finding another angle when this one's given? But more importantly, I think it's really good to use angles less than 90 degrees. If you're given this angle as 30 degrees and you want to use 120 here, then to me it becomes less obvious which is the sine, which is the cosine, which is the x component, the y component, because I don't know what the opposite and adjacent side of a 120 degree angle are. But I can look at a 30 degree angle and I can tell you the y component is the adjacent side, it's going to be cosine. The x component is the opposite side of that angle, it's going to be the sine. So for my x component, I'll put the numbers here in red. I got 3. And for my y component, I got 4. And for my y component, I got 6 in the negative direction. And for my x component, I got 2 in the negative direction. So I add these up. The x components, I've got 3 minus 2, 1. The y components, I've got 4 minus 6, negative 2. So I can draw my vector is going to have a x component of 1 and a y component of -2. And that's my C vector. So now I need to find an angle somewhere. I think I picked this angle earlier. I'll stick with that. So I know C is going to have a magnitude of the x component squared plus the y component squared square root. And that angle is going to be the inverse tangent of 1/2. So this tells me my C vector has a magnitude of 2.236, and it's in an angle from the negative y-axis of 26.57 degrees. When I do this, I always say a picture is worth 1,000 words. Just draw this picture, and I immediately know what angle you're trying to find, and then tell me what that angle is. If you're drawing a picture like this, and you've indicated an angle here, do not put a minus sign there, right? This number has to be positive. You've told me this angle is what you're measuring. Don't give me a negative angle if you're telling me this angle is what you're measuring. So when I take the inverse tangent, I'm taking the inverse tangent of this side, which has a magnitude of 1, over this side, which has a magnitude of 2. It's the inverse tangent of 1/2. It's the length of the side of the triangle. The length of the side of a triangle cannot be negative. So this is how I would report it on a test. I would draw that picture and put the magnitude and the angle. We can break vectors up into their components. We can add them graphically. We can add them using components. And there are two more operations we do with vectors. We have a vector dot product, which we've already used, and we have a cross product, which is still coming up. So if vector A and vector B are combined with a dot product, this is also called a scalar product because we take two vectors in and return a scalar. This gives us the magnitude of A times the magnitude of B times the cosine of the angle you get when you put their tails together. That would be theta in this case. The cross product takes two vectors and returns a vector. The magnitude of this would be the magnitude of A times the magnitude of B times the sine of the angle between them. And the direction is given by the right-hand rule. It's perpendicular to both A and B. So it's perpendicular to the plane defined by A and B. If these are my vectors A and B, the cross product would be perpendicular to the page. A cross B would give us a vector into the page. There are various ways to see this. We use what's called a right-hand rule in physics. I like to do it by taking the fingers on my right hand and pointing them in the direction of the first vector. My thumb is going to be the axis of rotation. So I'm going to rotate about my thumb. I'll point my thumb toward the camera. I'll rotate my hand from A toward B. If I rotate my fingers from A toward B, then my thumb points toward the camera. That would be the direction of the cross product. If I rotated my fingers from A to B and my thumb had to point away from the camera, then that would be the direction of the cross product. In this case, when I put my fingers in the direction of A, my thumb will point into the page when I rotate them toward B, because I always rotate from A to B through an angle less than 180 degrees. So in order to rotate my fingers from A to B, my thumb points into the page. If we reverse this, we would get the exact same magnitude for the cross product, but the direction would be opposite. My fingers would go toward B and rotate toward A, and my thumb would have to point out of the page in order to make that work. So A cross B is equal to the opposite of B cross A. There are other ways to do the right-hand rule. Look online, look in the textbook. This is my way of doing it. We use cross products a lot later in the quarter and in subsequent classes also.